everyone. I hope you're all healthy and well. Welcome to the next talk in our Golden Webinars in Astrophysics series. Our speaker today is Alexey Vikhlinin, who's a professor at the Harvard Smithsonian Center for Astrophysics and co-chair of the Science and Technology Definition Team of the Lynx X-ray Observatory, which is one of the new great observatories. My name is Thomas Puzia, and together with Evelyn Johnston, we have organized today's webinar for you. As in our previous webinars, we have arranged again for simultaneous language interpretation by Mr. Patricio González, who will be simultaneously translating for us into Spanish. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana Zoom y seleccionar Español. We would like to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA, for its Spanish acronym to support this series.
Thank you so much for all your feedback and comments. If you're watching a recording of this talk, please leave your comments below. And if you would like to support the Golden Webinar series or give us feedback, please send us an email. If you have any questions during the talk, you can type them into the Q&A window, where you can also upvote questions and comment on them, and we'll select the best questions for the discussion after the talk. Before we begin, I'd like to briefly introduce our other panel members today. From the faculty at the Institute of Astrophysics at PUC, we have Ezekiel Triester. We also have our students and postdocs, Enrique Paillas and Paul Eigenthaler. And we have the great pleasure to welcome our guest panelists today. We have Rohan Rahat-Gaukar, who is a recent graduate student from the University of Toledo and an intern at Gemini Observatory. Fabio Vito, who is working at the Scuola Normale Superiore in Pisa in Italy. And Maurizio Paolillo, who is a professor of physics and astronomy at the Department of Physics Ettore Pancini at the University of Naples. And finally, we have our excellent team of Q&A managers, Ricardo Acevedo, Daniela Fernandez, and Carol Rojas.
It is our pleasure to introduce Alexey Vikhlinin as our speaker today. Alexey studied for his degree in space physics at Moscow Institute of Physics and Technology, graduating there in 1993. He later gained his PhD in astronomy from the Russian Institute of Space Research in 1995. He joined then the Smithsonian Astrophysical Observatory, or SAO, initially as a postdoctoral fellow in 1986, and later became an astrophysicist at the Center for X-ray at the Chandra X-ray Center in 2001, and then as a senior astrophysicist and deputy associate director of SAO's High Energy Astrophysics Division in 2013.
His research focuses on the astrophysics of high energy phenomena, namely galaxy cluster cosmology and the design of space-based X-ray observatories. He was the co-chair of the Science and Technology Division team for the Lynx X-ray Observatory, a NASA-funded large mission concept study under consideration by the 2020 Decadal Survey on Astronomy and Astrophysics. Today, Alexey will tell us about his work on Lynx, his Revolutionary X-ray Observatory. So Alexey, over to you.
Thank you very much. Thanks for this invitation. I'm thrilled to tell you about Lynx. Here we go. So let me just put this work on the X-ray Observatory in perspective. So what's happening in US now is what US astronomers do every 10 years, and it's called a Decadal Survey. A Decadal Survey is a large number of panels, scientists working on trying to figure out, trying to understand, predict, and you know, systematize the input from a large number of scientists. Basically, the goal is to predict what the science priorities would be in the next 10 to 20 years, and maybe recommend specific projects both on the ground and in space. And NASA and other US science agencies such as NSF take input from the Decadal surveys very seriously. Typically, what's recommended, top recommendations of the Decadal surveys are implemented. So in space, large projects are very expensive. JWST, for example, James Webb Space Telescope, is going to cost somewhere around $9 billion when it's finally launched. So developing projects like this takes more than just, science inputs, more than your fantasies. It's a lot of really detailed work on science requirements, on designs, on assessing the state of technologies, assessing, the schedule and cost of this future project. So to do all this work, NASA in 2016 formed 4 teams, the science and technology definition teams for 4 projects, which are now basically competing for the top recommendation in the ongoing Decadal Survey. Maybe Decadal Survey recommend a series of those, and we call them, new great observatories. But basically, these 4 projects are, top contenders for the NASA recommendation, and Lynx one of them. You can learn a lot. Basically, you can learn everything there is to learn about this 4 concept on the website called greatobservatories.org. It has documentation, convenient links to documentation generated by each of these 4 mission studies. And it gives you ideas of what, these observatories can do together if they launched in parallel or in sequence. Just to name these 4, it's LUVOIR, Large UV Optical and Infrared Telescope, whose goal is, it's basically, very large diameter general purpose observatory that can look for biosignatures in habitable planets around nearby stars, as well as doing a large range of normal astrophysics in the optical and UV. HubX, this focuses primarily to do habitable planets, but also some of astrophysics. Origins, this is a far infrared observatory. And the normal focus is, what is done in those wavebands. And Lynx is the X-ray Observatory. So I'm going to tell you today about Lynx. Let's start just by noting that X-rays, in the X-rays, one observes the sites of the most energetic energy releases, most powerful energy releases in cosmos, as well as baryons, a very significant fraction of cosmic baryons. So X-ray observations are really needed to are required to understand the cosmos. X-ray astronomy has a rich history, but it's a very recent history. So the father of X-ray astronomy, Riccardo Giacconi, just passed away a couple of years ago. Here he is in 2012. After receiving the Nobel Prize, he's recalling his first measurement from a sounding rocket. So his team launched a very simple detector just to scan the sky in the X-rays. So in this very first flight, they discovered 2 things. A large bump here over the background, that's a very powerful emission from a neutron star in a binary system called Scorpius X1. Here you see that the level of measurements in the detector that looks at the sky is higher than the level of counts in the detector that measures the background. This total emission, called the X-ray background, is basically, now we understand that this is a total emission from a large number of active galactic nuclei, basically supermassive black holes at cosmological distances. So it's amazing, with very simple instrumentation. On the very first flight, you see neutron stars and you see emission from black holes, right? And that was in 1962. In 1999, the current state of the art has been launched. This is Chandra X-ray Observatory. With Chandra, we have fantastic mirrors that focus X-rays almost as well as optical telescopes focus optical light. And And we can see the power of Chandra to look at objects from, for example, this comparison. This is an optical image of from Sloan Digital Sky Survey. And it has, it has galaxies, not very distant, but it has a quasar at a redshift of 6, which is visible as a small red smudge over here. So redshift of 6, this is very, very far away. This is basically the universe exiting the dark ages, and normal galaxies just starting to form. Black hole has an estimated mass of 1 billion solar masses. It's it's visible, but not that great. In the X-ray image obtained by Chandra, this is the brightest objects in the sky region. Okay, Chandra, total collecting area of Chandra is the same as area of an optical telescope with about 30 centimeter diameter. Some of us might have such telescopes at home. So it's amazing in an X-ray with an instrument like that, with collecting area that small, that you're able to study black holes. You can unambiguously identify black holes, and you can observe them to great distances. So upcoming telescopes, facilities on the ground and in space, such as JWST, or a new generation of 30-meter, very large optical telescopes, they open both, a great opportunity and pose a great challenge for the future X-ray astronomy. The opportunity is that after these upcoming observations, X-ray studies of, for example, first black holes or detailed mechanisms of galaxy formation would be a logical next step. The challenge is that the capabilities that would be required to match upcoming facilities in the optical and in radio, they require the gain in capability of Chandra by some 2 orders of magnitude. And so this is a very huge change. And until recently, such advances were simply not technologically possible. So now let me show. Let me illustrate with this movie the main technological challenge, and that's how you focus X-rays. X-ray cannot be focused in normal incidence like you do with the optical light. They are only reflected from heavy metals if the incident photons come at a very shallow angle. We call it grazing incidence. And so what you see is a schematic of Chandra mirrors. So instead of building a large mirror like in the optical telescopes, you have to have a nested system of these shells. Okay, each if you look from along the input aperture, you will see only a small fraction, because you really, those mirrors are inclined at maybe 1 or 2 degrees with respect to incident photons. So you have to pack a lot of them to get, substantial effective area. But other than that, optical scheme is pretty similar to, normal telescopes. You have a primary and you have a secondary, so you have 2 reflections, and then the photons get focused on the detector plane and you form an image. With detectors, you can, in the X-rays, you typically can detect individual photons. You can measure energies of individual photons. So you can get a lot of information. The trick is to focus all these photons very nicely. Here is an illustration of how tight the requirements on the quality of X-ray mirrors are. So Chandra is the state of the art. So they had to be polished. The Chandra mirrors had to be polished so smoothly that if we magnify Chandra mirror to the size of country of Chile, okay? So the bumps on that mirror will have to be smaller than about 20 or 30 centimeters. So it has to be flat, basically smooth over this entire, length of the country of Chile with only tiny bumps. This is how smooth the X-ray surfaces should be. And if you pack a lot of them in a small volume, you have to obtain such surfaces on thin substrates. So you have to provide structural stability, and you have to have a mechanism on how you produce such lightweight and very precisely polished surfaces. So I will talk about technologies for achieving this at the very end of the talk. But basically, what the requirements, what I described now, were impossible to achieve only a couple of years ago. And what happened during the course of Lynx study is one of our technology teams basically figured out the way how to do it. And they've demonstrated that they can make mirrors that basically meet the requirements for the observatory. Anyway, so now, thanks to a lot of technology investments in the US primarily, an observatory like Lynx is totally feasible. So here is Lynx. It's an observatory that built on a proven architecture. It will provide giant leaps forward. It will especially be strong in the 3 science areas, which we call the science pillars. And these areas are used to drive the requirements of the observatory. So the areas are dawn of the black holes. We call them the dawn of the black holes, the drivers of galaxy evolution, and the energetic side of stellar evolution. So let me go through these areas, explain what we aim to observe with Lynx, explain where requirements are coming from, and it will give you a sense of power of this observatory already. Then I will give a couple of unexpected science examples, and towards the end talk about technology for making the mirrors. So the dawn of black holes. What you see in this slide is an artist concept, basically a computer-generated detailed image of a black hole, of a big black hole in a galaxy. And until recently, we had to use those images. Now we have an observation that basically shows an image like this in real life. So I'm going to play the zoom in movie from the Event Horizon telescope. And that would put the black hole science in the context. So somewhere in the constellation of Virgo, there's a big cluster of galaxies. There's a big galaxy in the middle. And so we are zooming in. We see outflows, hot gas around this galaxy. We see the jet. We see finer and finer structure of this jet. And here we go, the shadow, right? So this unambiguously establishes that there is a big black hole in the middle of that galaxy. From the size of the shadow, you can tell what the mass of that black hole is. It's a few billion solar masses. Well, how do you make black holes that massive? Turns out that a black hole in this galaxy M87 is not difficult to to grow to this mass. You've seen during the zoom in that this black hole outbursts a lot of energy, right? Jet outflows. It has strong emission in the optical, also in X-rays, across the wavelength spectrum, in the radio. So you can compute how much energy is coming out. This energy is being generated by the material falling in. So it's a gravitational energy of the accreting material that provides, all these powerful effects. And so we can compute based on, the output, we can compute how much material is coming in per second. So it turns out that if black holes like this grow during, the time of evolution of the universe, there's enough time to grow them to, a few billion solar masses. What's very surprising, though, is that black holes with mass not much smaller than the one in M87 are now discovered very early on in the evolution of the universe. So on one slide, I showed the black hole at redshift 6. The record holders are now at redshift of 8 and also approaching in mass to the a billion solar masses. Now, there's a limit. We think there is a limit at how fast a black hole can accrete material. Basically, if it accretes too fast, the emission that is generated will exert the light pressure, which will exceed the gravity of the black hole. And at this point, the material should stop forming. No more energy is generated. Right? We call it an Eddington limit. So Eddington limit, give or take, should give you within a factor of a few, maybe the maximum rate at which the black hole can acquire mass. So it turns out that there's almost not enough time from the Big Bang for the black holes, to grow to 10 billion solar masses at a few hundred million years after the Big Bang. That's where we observe them. So something interesting must be going on. It could be they can start as remnants of explosions of very massive stars, but then you will have to arrange special modes of accretion where the Eddington limit is not applicable. Or they could be what we call heavy seeds, a product of gravitational collapse of big gas clouds, or maybe runaway collapse of dense star clusters right into black holes with mass of about 100,000 solar masses. I should say that a formation of a black hole, almost instant formation of a black hole with a mass of 10 to the 5 solar masses should be one of the most spectacular, maybe the most spectacular event in the history of the universe. So much energy generated in such a small time. So how do we establish what is the origin? What is the initial seeding mechanisms for the black holes? Some of the panel members try to do this studies with Chandra, look for very massive black holes very early on. And we know it's hard. The sensitivity of Chandra is simply not enough. So what is needed is an observatory that will provide a sensitivity to be able to detect black holes with this mass range right at the epoch where we expect them to form. Okay, and this is basically this is our main requirements for the Lynx sensitivity. So it is designed to be able to look at black holes with masses of 10,000 solar masses at redshift of 10. And by comparing X-ray images from Lynx with optical and infrared images from JWST, we will be able to tell in which galaxies at high redshifts we see, this earliest generation of the black holes. Just to drive home back. So zooming in a little bit on the simulated, on predicted Lynx image of a small 2x2 arc-minute size. So we see lots of sources, some of them coming from active galactic nuclei in low redshift galaxies, and some of the high redshift galaxies are, populated with heavy-seeded black holes, according to one of the realistic scenarios of the black hole formation. And as you can see, there is enough sensitivity for Lynx to see emission from those sources, and by cross-correlating properties of X-ray emission and optical emission seen by JWST, we will be able to say pretty confidently what is the formation mechanisms of the black hole seeds. Now, the sensitivities we're talking about here are pretty astonishing. So this image, the expected exposure is about 1.5 months, and the faintest sources would have about 10 photons. So roughly, we are collecting about 1 photon per week from a very distant objects. We're still able to confidently detect this emission, and not only detect, but use its properties to say what is the origin of black hole seeds in those incredibly distant galaxies. So sensitivities like this, they just emphasize the power of X-ray astronomy, how much information per photon we are extracting from the data. Now let's turn to the second driver, the second pillar, science pillar, that's drivers of galaxy evolution. So now exquisite data is available already on stellar dust and cold gas content of galaxies, but the exact mechanism of how galaxies, this major building blocks of the universe, there's no single theory that actually describes exact formation mechanisms. And this is illustrated well by numerical simulation that try to produce realistically looking galaxies. So what's playing here is a simulated box done by the same team with slightly different physical assumptions. And what you see here is evolution of the gas, diffuse gas density on the left, gas temperature in the middle, metals, and then the galaxies are on the right. You shouldn't be able to see almost any difference between the galactic properties. That's because the simulation physics is tuned to produce observed optical properties of galaxies, right? So where do you see the difference in physics? First and foremost, in the temperature distribution of the gas, in the metal output, somewhat in the density. I think it's pretty clear from looking at these pictures that in the optical, we basically see the consequences of the process. We see the consequences, the outcome of galaxy formation process. The drivers are imprinted in the diffuse gas, and primarily you see these drivers in the X-rays because the gas is heated to hot temperatures. That's another illustration of what is expected and how one can learn about galaxy evolution. So what's plotted is expected energy ejection modes for galaxies of different mass. So as we go down in the mass hierarchy, go up rather, we see changes in what we call the energy feedback. So a lot of energy need to be ejected into the gas component to explain the properties of those galaxies. And the mechanisms of this energy ejection are different for galaxies of different mass. From supernova explosions to powerful feedback from powerful energy outputs from the central black holes. And they result in very different properties of the cold and warm gas, but also very different properties of the hot gas. Hot gas is what one observes in the X-rays. Cold and warm is what's observed in the UV spectroscopic studies. Here is another illustration of how powerful the X-ray measurements will be. This is called the phase diagram. So that's basically you simulate a box, a cosmological box, and you put points. Each gas parcel, gas point is, has its temperature and density, and you put those points in the gas versus temperature diagram, and the brightness tells you, how much gas is basically at those conditions, right? So the phase diagram. So this is how the simulation box looks, and this is a phase diagram, right? So this is what you observe in the optical. So you observe stars, the very condensed material, and you observe a small amount of gas around cosmic web filaments in the galaxies. In the optical, in the UV light, you observe some cool gas around, or warm gas rather, around galactic halos. In the X-rays, through absorption and emission, you observe this. Right, most of the volume is in fact filled with hot gas. This hot gas records all the properties, records the output from drivers of galaxy formation. And just to illustrate again a comparison. So what the movie runs the evolution of the warm gas and hot gas around one of the galaxies. So you see different sides of the galaxy formation process. You cannot see everything in a single waveband, but most energetic drivers and most of the physics is encoded, in our opinion, in the X-ray view of galaxies. So Lynx is designed to, to be able to see hot gas around galaxies and the cosmic web, both in emission and absorption in long observations. So we should be able to really take good measurements of the, which basically tell us how galaxies, as we observe them today, come to be. The third pillar is the energetic side of stellar evolution. So we are now in the era of multi-messenger astronomy. We see signals in the gravitational waves, planet studies. They evolved to holistic assessment of habitable conditions from just doing single detections, and to understand galaxies and cycles of elements, you need great leaps in data on star formation, and so studying stars and stellar population is also multi-wavelengths, multi-messenger process, and the science need include observations of high energy processes, which are associated with stellar birth, life, and death. And Lynx will uniquely provide those capabilities. A few illustrations. So it turns out that X-ray images are, great ways to find young stars and young star-forming regions. Basically, when stars just are born, for a few tens of millions of years after birth, they rotate fast, and as they rotate, they generate a lot of coronal emission, which is seen in the X-rays. In fact, with Chandra, you get one of the best and most complete samples of young stars in nearby clusters. The trouble is with Chandra, the science horizon, the sensitivity is enough only to look at this region of the Milky Way. There's only one massive and actively forming star formation region in this volume, and that's the Orion Nebula, right? To study regions with different range of masses, metallicities, formation rate, conditions, you need to go much further. So the sensitivity will be provided by Lynx, and with Lynx we can reach into nearby spiral arms with, much more powerful star formation, regions of star formation. For supernova remnants, this is a great topic for X-ray studies. Basically, current instruments provide a projected view of a supernova remnant. You can, if you look with Chandra, for example, you can separate the spatial projected distribution of different elements but it's really tough to measure velocities or measure, fine changes in the metal abundances or ionization states. Lynx will be equipped with an X-ray microcalorimeter with pixel size matching the angular resolution of the mirror. So with microcalorimeter, you have an enormous increase in the energy resolution. So instead of projected excess in energy like this, we expect the same object to produce data on individual lines like this, where you have fine kinematic structure as well as a full resolution of different ionization states. Supernova remnants with Lynx, there will be enough sensitivity to take the studies extragalactic. This example shows what one can do by surveying, for example, the M33 galaxy. So in the optical, we are already getting very detailed data, but with forthcoming telescopes, we will get a really detailed picture of star formation in this galaxy. And the supernova remnants, they track the supernova response to the star formation process, within the last 10,000 years or so, right? With Lynx, one can determine types of parent supernova explosion, core collapse or type 1A explosions by multiple means, by morphology, by looking at spectra. Basically, you expect different mix of elements in supernova explosions of different types. So you can do typing of supernova explosion, and so you can really track a relationship between supernova activity and star formation activity in a galaxy other than the Milky Way. All right, so let's now talk about capabilities. So the three science pillars, the science needs for the three science pillars, they really call for drastic increases in science capabilities. And one of the ways to compare it is to look at the gains along different axes compared to current state of the art, which is Chandra. Right, so for example, this plot shows if Chandra effective area is normalized to 1, then the Lynx effective area will be a factor of 30 higher, right? The sensitivity of Lynx is more than 2 orders of magnitude higher than the sensitivity of Chandra. Grating spectrometer will provide almost 3 orders of magnitude more effective area for spectroscopy than the Chandra gratings. Chandra doesn't have, it only uses CCDs to measure photon energies in the imaging mode. So the energy resolution is not great. It's like using in the optical just narrow band filters. The microcalorimeter on Lynx will provide a 2.5 orders of magnitude improvement in the energy resolution for individual photons in the imaging mode, right? That also translates to almost 2 orders of magnitude increase in the data cube size. So if you add up all the imaging pixels and then the spectroscopic resolution elements, factor of 100 more data, per observation will be collected using Lynx than compared to Chandra. So these are huge improvements across the board, right? And so when you have improvements by 2 orders of magnitude, I would submit that this is really, we're talking about almost opening a new waveband for observations. There's in many areas we simply don't have a sense today from current instruments. We don't have a sense of what Lynx will be able to observe, because Lynx will be a factor of 100 to in some cases 1,000 more powerful. And what we expect though is that now with these capabilities, the impact of Lynx will be felt not only in the areas which are traditional for X-ray astronomy, but it will be felt by throughout the astronomical field. If you do stars, and you never thought about using an X-ray telescope, you might want to rethink this approach, because this will be something interesting that Lynx will do for you. So let me give you a couple of unexpected examples. And the one is epoch of reionization. Epoch of reionization is period of time in the evolution of the universe between just before the first generation of galaxies reheated the intergalactic medium and reionized intergalactic medium. So basically, during the epoch of reionization, we see the transformation of the universe from diffuse, gas, dark phase after the Big Bang, after the generation of the cosmic microwave background, and just before it enters, today's an evolutionary stage which is similar to today's universe, with galaxies, working, black holes working, and so forth. Right? So this epoch of reionization is identified as a huge discovery potential areas for a number of years. There's a large number of experiments being built to try to observe the universe during this time. The primary signal from this epoch is a 21 centimeter hydrogen radio line, which is redshifted to long wavelengths. So long wavelengths radio is the primary way of observing this universe. So what can X-rays do for, how X-rays can help do this? Turns out that the X-ray output from the population of X-ray binaries in the very first galaxies is projected to have a huge impact on how exactly the reheating of the universe proceeds. The reason is the X-rays are much more penetrating than the UV light, so they will not be trapped right around the galaxies. They are expected to travel to large distances and preheat the intergalactic medium before it gets ionized. And so these are computer simulated predictions on how the universe, the distribution of gas and temperature will look like as a function of redshift for two models with normal X-ray output or with extreme X-ray output. And you can see the evolution proceeds very differently. So what it tells you is to interpret, to get maximum of the data from reionization, from your radio measurements of the epoch of reionization, you will need to know what the X-ray binaries are doing at this redshift, right? And so this is where Lynx comes in. So it will have the sensitivity in the deepest surveys to track the evolution of X-ray binaries, integrated X-ray output from galaxies out to redshift roughly 10, so just before the onset of epoch of reionization. And this will be really crucial to normalizing our models for what the X-ray binary population will be doing. And there is hope to, by cross-correlating the residual background in Lynx images with radio signals, to see, X-rays, to maybe detect X-rays coming right from the epoch of reionization at redshift 15 or so. So this is the largest scale, the furthest distances. Now let's look at the probably smaller scales. So how one can use X-rays to measure stellar masses. And stellar masses is really, for me, it was really a unexpected realization that the direct measurements of stellar mass are only available in our own solar neighborhood through dynamics of stars in the binary system. Everywhere else, stellar mass is not measured. It's an inferred quantity. So there's a nice quote from Carlos Frank here. Nobody ever measures the stellar mass. This is not a measurable thing. It's an inferred quantity. You measure light, okay? So you can measure light in many bands, but you infer stellar mass. Everybody seems to agree on certain assumptions that are completely unproven. That's a strong quote from one of the most prominent astrophysicists living today, right? So turns out that the microlensing of background quasars is the only direct way, only known direct way of measuring stellar masses beyond our solar neighborhood. So what happens here is, if the background, if the quasar is behind the lensing galaxy, the stars within the galaxy will move, and they will move the caustics. These are regions of maximum amplification of by gravitational lensing, and so we expect, the models show that we expect orders of magnitude variations of brightness when the stellar field in the lensing galaxy shifts by only tens of microseconds. And so by observing fluctuations of these multiple images, you will you have means of measuring the masses of stars. So microlensing gives the full mass in the galaxy. Microlensing, this flickering, gives essentially the mass in stars. Chandra results based on a small number of systems is within a factor of 2. The mass to light ratio in stellar populations looks like what you expect from the salpeter initial mass function model. The Chandra is limited by statistical quality of tracing the flickering of background quasar, and also by the number of systems that is observable. So after the LSST, the Vera Rubin telescope survey, we will have a huge increase in the number of quadruply lensed quasars. And with Lynx, we will be able to track those microlensing light fluctuations much better. So we project that the stellar mass measurements with this technique will become exquisite after the LSST. So who would, would you expect that, the best way of measuring stellar masses directly is to use an X-ray telescope? All right, so in the concluding minutes of the talk, let's talk about the observatory and the technology breakthrough. So the observatory looks like a typical X-ray. Our concept for Lynx looks like a typical X-ray observatory, like Chandra. So we have an X-ray mirror with 2 square meters of effective area, subarc second point spread function over a wide field of view. In the focal plane, we have 2 detectors, and also in between we have gratings. So there are 3 science instruments we call high definition X-ray imager, the microcalorimeter that has 1 arcsecond pixels covering a 5-degree field of 5 arc-minute field of view, and 2 subarrays for additional capabilities. And there is a grating spectrometer, so gratings can be inserted in the light path between the mirror and the detectors, and they provide exquisite resolving power and high efficiency to do fine spectroscopy. So observatory would be launched at the Sun-Earth L2 point. It's designed to be able to look at 85% of the sky at any given time. So for anything interesting happening, like a gravitational wave event, there's a good chance that Lynx will be able to point, very promptly. Consumables are sized for a 20-year mission. So consumables you need to maintain the orbit around the L2. This is what limits the lifetime. So at least 20 years observations. And observing efficiency over 85%. So over 85% of the time, we should be able to look at cosmic objects. So now let's talk about the mirror. So 2 square meters of effective area translates into something like ELT worth. So the 30-meter diameter mirror, 40 meter diameter of an optical telescope. So huge polished area. So how do we do that? So a team at Goddard led by Will Zhang, in the past several years, they perfected the process. You basically build those mirrors as thin segments from commercially available crystal silicon blocks. So not very expensive. And you can use different stages of their process, right? And conceptually, it's not very different from what Galileo was using to polish his first mirror, right? Something rotating, and you push your substrate against something rotating out here. The only really high tech step of the process is here. It's called ion beam figuring. So at the end, now there is a very efficient way of really bringing your surface down to design shape by removing a few nanometers of materials here and there without sacrificing the surface quality. And so this mirror is built out of segments. Lynx mirror will be built out of segments, and segments are much easier to handle individually than big mirrors like the ones used in the Giant Magellan Telescope. In fact, at some stages, it's perfectly fine to just hold the material by hand, as you can see, right? And so this is very efficient. They know what it costs to make one segment, how much time it takes. So you go through all this, and a block turns into a segment of high quality mirror and the residual block. Residual block can be sent to the beginning of the process. After a while, you end up with another segment. Again and again. And it can be repeated. It can be run in parallel. So you can produce many of those, really many of those, in a manageable amount of time. So after this segments are produced, and the Lynx mirror has nearly 40,000 segments. The segments are put in the modules, mirror modules. So roughly 600 mirror modules, so roughly 50 meters, 60 meters per module. The modules are built into on a ring-like support structure, and we call it metashells, right? So at this point, at the metashell stage, conceptually it's the same as this barrel-shaped Chandra mirror, and then the metashells align to form a single assembly. So from engineering point of view and from production point of view, you really should think about it the other way. So it's a single assembly split into 12 metashells. Each metashell has about 50 modules. Each module has about 60 elements. So it's a very hierarchical structure. And at each level of the structural hierarchy, you don't have more than like 50 elements, 60 elements. And I would submit that it's not a huge engineering challenge to be able to put 50 structural elements together so that they produce 0.5 arcsecond angular resolution image. So we believe it's doable. This mirror is mass producible. The design is modular, and the process is parallelizable. So we can do it in a few years' time. it will take a few years to build the entire Lynx mirror assembly. All right, so just before I conclude, let me emphasize again what kind of gains we expect to see. So the imaging component, just comparing the Chandra deep image with what we expect from Lynx on the right, it's a striking difference in terms of depth and in terms of uniformity of coverage, right? So once again, we expect to have 0.5 arcsecond PSF on axis. That's our requirement. 50 times Chandra's throughput in the soft X-ray band. So more mirror and better detectors will provide 50 times the throughput. The optical design for these mirrors, because they are short and because they can be positioned better than the Chandra mirrors, it will provide more stable point spread function across the field of view. So we expect the sub-arcsecond PSF throughout the 20 by 20 arc-minute field of view. And with Chandra, we only had better than 1 arcsecond resolution in the central area of the field of view at with radius of 1.5 arc-minutes. So the area where we expect good imaging is about 20 times that what's provided by Chandra. So if you combine gains in the throughput and in the coverage, it's about 1,000 gain compared to Chandra in survey speeds. So that's a factor of 1,000 improvement in your ability to do high redshift science or to do stellar clusters in the local universe. The spectroscopic components, it calls for similar dramatic gains. The grating spectrometer, for example, as I mentioned, at nearly 3 orders of magnitude of Chandra throughput and almost an order of magnitude in resolving power. So from spectra like this that we observe today, with multiple lines in the stellar corona blended into bumps, we will expect to reach into spectrum like this, with individual lines fully resolved and physics can be inferred from those. With the X-ray microcalorimeter, we will basically complete the evolution of capabilities which would be parallel to the evolution in the optical, from the first astrophotograph or the earliest X-ray images to state-of-the-art imaging with Hubble Space Telescope to really hyperdimensional data sets which can be obtained with instruments like the Muse spectrograph on the VLT. So Lynx will complete this step in X-ray astronomy, from going to Chandra to Chandra-like images with spectroscopic quality data provided by the X-ray microcalorimeter. The gain is really equivalent to what you expect from going from a leap will be equivalent to what you experience from going from 1980 epoch, optical telescope 1 meter diameter to the VLT 8 meter VLT equipped with Muse. This is the same gain that Lynx will provide over Chandra in terms of imaging and spectroscopic capabilities. So it will be huge. So anyway, I want you to wish us success. The US Decadal Survey is ongoing. They expect a decision to be announced in the spring of next year. So if Lynx is prioritized, if it's one of the recommendations, it potentially can be launched in 2036, so in the second half of 2030. So the younger people in the audience will have an opportunity to use it for their own science and to see how transformational the telescope is. Thank you very much. Let's do questions now.
Thank you, Alexey. Do we have any questions from the panel?
Can you say a couple of words about the next steps Lynx will go through before NAS adoption?
Mm-hmm. So assuming it's recommended, what typically, here is how I understand the NASA process for developing the missions. So for a couple of years, it's they run what's called pre-phase A process. So even before you formally start the project, you have a period of time where you mostly maturate the key technologies. So we have a small number of technology gaps compared to the other concepts. So I mentioned the mirrors. So in the mirror area, what we think we have proven is that individual segments can be made, and the two segments can be put on a support structure in a line so that they produce arcsecond quality mirror. What we have not proven yet is that one can build a module of 50 such mirrors, and still maintain arcsecond quality. So it will take a few years and dedicated funding to do this work. So that's mostly what's kind of stuff that's done in pre-phase A. Then NASA runs a phase A for a year or two. In the phase A, based on you conclude development of technologies, and you also produce pretty detailed engineering concept for the mission. And that engineering concept will be suitable for getting the precise cost. So at this point, you either design with a cost goal, right? Or you understand what the cost will be given, the science capabilities. So typically there is a trade-off between the two. So at the end of phase A, we expect, to have an engineering concept with pretty good understanding of the cost. In phase B, which runs for another couple of years, you now produce a really detailed design and manufacturing plan. So the project gets a formal go-ahead at the end of phase A before it enters phase B. And then phase C is basically production. Your production. Phase D is assembly and testing and launch. And then phase E is operations. So initially, everybody puts 5 years of operations with the understanding that those observatories can operate for a long time.
Okay, let's go to Rohan next.
Hi, thank you for a wonderful presentation. So I have a question similar to one in the top of Q&A from Emmanuel Pompey. He asked, how does Lynx compare with the incoming ESA mission Athena? And my question was, as you might know, to prevent the 12-year blank period in soft X-ray astronomy, there's missions such as the XRIMS, which is to replace the Hitomi mission. So how would those missions results have any impact, if any impact, on the Lynx and Athena mission?
Okay, so let's talk about Athena. Athena. So this is a plot, we call it the spider diagram. This is a plot where we plot capabilities relative to current state of the art, relative to Chandra. And if you can see colors, this bluish shade is the Lynx growth and capabilities, and the red is Athena's, right? And so Athena is approved. Athena is going forward. Athena will not have arcsecond quality imaging. So the goal in angular resolution is 5 arcseconds. And with 5 arcseconds, you cannot reach high sensitivities because of the source confusion effects. In fact, source confusion for Athena will kick in before it reaches the flux levels, which are now achievable with Chandra. So Athena is simply not designed for high sensitivity studies, high sensitivities. it's designed with different set of science goal in mind, right? So you can almost see that the most of the gain that Athena does compared to Chandra is in the opposite direction. It's in the field of view, which provides ability to run, very large surveys of the sky. It has high effective area at high energies, so this is a capability of doing measurement of things like iron line from the black holes. So Lynx and Athena are really very complementary missions, orthogonal missions, missions with different science goals. So we are very pleased that Europe is going forward with Athena. It will not, Athena is not, is not eating our pie. It's not, it's not competing directly with Lynx. They really are going after fundamentally different science focuses. Now, smaller missions like XMM or Spectrum X Gamma, which was launched last year, they are even more focused. So XMM, for example, the main focus is to finally have one, X-ray microcalorimeter working for a long time on a spacecraft, right? So it will provide huge increase in resolving power, but it will only have 16 imaging pixels in the field of view, right? So we're not talking about really taking detailed images. So again, XMM is good for, doing either spectroscopy, detailed spectroscopy of bright, point sources, or maybe, several regions and extended objects, but really, not much more. Spectrum X Gamma, it runs surveys, but doesn't do, much else. So Lynx is really observatory class, great observatory class, like the Hubble Space Telescope in the optical band. And so there are many areas in research where other facilities, can be used.
Thank you.
Mm-hmm.
Okay, let's go to Enrique next.
Okay, thank you very much for the wonderful talk. So I was curious about what is the probability of success of the launching process of such an observatory into space? Like based on previous missions, is there any significant chance of running into some, say, catastrophic failure? Like, do we still have to cross our fingers, or is it very unlikely for something like this to happen nowadays?
Yeah, that's a great question, actually, Enrique, and I didn't cover it. Forgot about it or ran out of time. First, let's know that Lynx design fits into normal rockets. It doesn't need a new generation of launchers to launch it. So the mass is 10 tons. The diameter of the mirror system is 3 meters. That fits into, in terms of weight and in terms of volume, it fits into almost serially produced rockets today, right? So things like Delta IV launcher in the US has been used multiple times. It's used to launch multi-billion-dollar military satellites pretty routinely. So there's always a chance in the space research that the rocket blows up. But in terms of, really state-of-the-art capabilities, Lynx does not require any. Stability of the pointing is the same. Requirement for stability of the pointing is the same as Chandra. So it has been achieved, it has been demonstrated. Mass very similar to Chandra. Thermal requirements, how well the temperature should be controlled and what level of temperatures on the spacecraft, same as Chandra. So basically it's been, it's been done, it's been proven, it's nothing out of extraordinary. All of new development is really concentrated in, into making a mirror and some packing many microcalorimeter pixels in a small volume.
Thank you.
Mm-hmm.
Okay, I think Ezekiel had a question next.
Yes, well, thank you very much. And thank you very much, Alexey, for a very nice and very interesting talk. I have a question that maybe is a bit too early to ask. Many of the scientific goals of Lynx will require significant observing time, right? And in particular, I'm thinking about looking for the black hole seeds, for example, will require large surveys with a lot of observing time. So are there plans or discussions about what fraction of the time will be devoted to, let's call them key projects versus regular PO observations? And I don't know if I have another question, but maybe later. Or no, up to you.
It's a great one also. So what we've done, we outlined, the science program, and you can find the report, on the website that I mentioned in the beginning. But basically, doing the science pillars will require, execution of multiple science program. Our vision is that only maybe the deep surveys, because it's a multi-purpose, investigation, would be pre-allocated. Everything else is competed. So we believe that, when this is the most efficient way of using the facility. And if the science goals will remain as exciting as we, believe them to be in 2030s, right? So people will want to run this kind of observation. So proposals will naturally execute the program. So in terms of what we outline in the report, we estimate roughly 50% of the Lynx observing time available in the first 5 years. So the other 50% is basically for something unexpected that we don't even, what it would be, right? The deep surveys program, for the black hole seeds, I know this is very close to your heart. So it's about, I'm just trying to quote from memory. I think it's a 25 megasecond program total. So it's a survey over a square degree. It's like wedding cake, typical wedding cake strategy. So a couple of deep pointings and then shallow pointings over a square degree. So only this part, which is roughly 1 year worth of Lynx observing time, probably would make sense to allocate as a key project with open access. Everything else, I think it's a lot more efficient to run in fully peer review mode.
Excellent. Thank you very much.
Okay, I'm going to go to the Q&A now. So at the top of the Q&A, there's a question from Robert Nikuta. I was wondering if 3D printing is anywhere near what's required in terms of smoothness, thinness, and stability for the reflective cylinders, and will 3D printing ever be good enough?
So interesting that you bring up this. So 3D printing was not envisioned for the technology I described today, but we in fact have two more viable technologies. They are not as far along as polishing of silicon crystals, but they are viable, and they also make good progress. So who knows? Maybe if Lynx is selected, the technology for making the mirrors will be different from what I've shown today. One of those technologies envisions putting piezoelectric control elements on substrates of some sort. Okay, and there is a reputable US company that has been looking. I know they have been looking at using 3D printing to make the substrates. So I don't know much. It's a commercial company, so they typically disclose only after they have full success. They have not disclosed yet, so I don't know what the status is, but I know they were playing with the 3D printing.
Maurizio, you had a question?
Oh, thanks, Alexey. I have two questions. One was about how confident you are that you can have a relatively uniform or sub-arcsecond PSF across large fraction of the field of view, that it's shown in part in your diagram. And the second I'm taking directly from the question and answer, because I had the same question. And is a question from Jonathan Quirola, who was interested in knowing if the satellite will have slewing capabilities and be able to follow up transient, for instance, that it's maybe a key science in the future.
Yeah, both are great questions. So the first one on the stability of the PSF, we are very confident. There's nothing magic. It's, you know, straightforward geometrical optics, you know, design. There's no, it's the reason why we project that Lynx is more is better than Chandra is because by nature of, you know, this mirrors made out of thin segments, the mirrors will be much shorter. Okay, so Lynx mirrors are 10 centimeters for the primary and 10 to the secondary. It's about 20 centimeters long. Okay, Chandra mirrors were 1.5 meters long. And the necessity of making Chandra mirrors long were related to manufacturing process. So they were polished from, you know, this thick blocks of glass, right? And so just the blocks are thick, so you cannot pack them tightly. So you have to have long mirrors, more, you know, widely separated. Right, and so Lynx mirrors are much closer to the thin lens approximation than the Chandra mirrors, and they're basically half of the way from, you know, in terms of stability of the PSF from Chandra to Lynx. And the other is with those thin mirrors, you now can implement a well-studied Walter Schwarzschild optical scheme instead of Walter 1. Which was used for Chandra, and you can also shift them a little bit axially along the axis to, you know, to make the focal plane, the best focal surface more uniform. The way we build detectors, also our detector technology for the high definition imager is, you know, is based on active pixel sensors, which so we envision many of those built to more smoothly follow the best focal surface compared to, you know, single big CCDs. So all those factors are, you know, there's nothing magic. It's, as I said, it's purely geometrical optics, you know, considerations. We looked very closely at, you know, structure, if it's difficult to implement or not, and it's not. So yeah, I'm fully confident if we build. If we can achieve 0.5 arcsecond resolution on Nexus, then we can achieve 1 arcsecond across the field of view. And the second question was on
the slewing capabilities.
Slewing capabilities. Okay, so we looked at we actually looked at this while doing the mission design study. So it turns out that so in principle, Lynx can point from where it is to 90 degrees away to a new position in about 40 minutes. Okay, so the bottleneck becomes now not how fast you react, but, you know, how you operate the telescope. So instant repointing is typically done on robotic instruments operating in fully automated mode. Okay, a $5 billion space, you know, project of that size, we expect no one will, you know, operate it in robotic fully automated mode. So the bottleneck will be on, you know, preparing a new command load to be sent to the orbit, availability of the contact window with the spacecraft, right? So we looked at different scenarios. Turns out that for about 15% of the transient events, Lynx could respond without introducing anything drastic. Lynx could respond within 3 hours. In some cases, maybe within a couple of hours to an event, and almost guaranteed within 8 hours. So This is it. So pretty, you know, I think it's a pretty decent response, but not, yeah, not instantaneous.
Before I ask the next question, can you stop sharing your screen, Alexey, so the audience
Sure.
can see you better? Perfect. So I'm going back to the Q&A. I've kind of got a double question. The first is from Matthias Wegner, who is asking, what is the data rate for Lynx? And my question connected to that is, will there be a data archive? Will the data be publicly available at some point in the future?
Mm-hmm. So data rate, I forgot in terms of you know, gigabit per day, but it's the same as JWST. So that I remember very well. We looked at you know, the data rate is the same as JWST. So there's nothing magic. You know, JWST is basically built, and there will be another 20 years of evolution of communication technology. So definitely not a challenge to send the data back. For archive, yes, definitely. We believe that the model that has been pioneered first in the X-rays and now used, you know, by Hubble and Chandra and everybody else is an excellent model. So maybe short proprietary period for you know, a person doing an observation, and then all data goes public and reused by, you know. So let me just give you another example. So with Lynx, you can reach the sensitivities of the Chandra deep fields in about 50 kiloseconds, right? So 50 kiloseconds is a typical length of an observation. So almost everywhere you look, you know, you will look at the object, but the rest of the field of view can be used as an archival data set with the depth equivalent to the deepest Chandra observations routinely. So it will be a hugely rich data set.
Cool, thank you.
I have one more question. So actually related to what you just said, will Lynx be the first telescope that will be capable of doing a complete volume limited survey that is limited by the universe? Of X-ray sources, of course, in this case.
X-ray sources, yeah. Well, for different types, right? So you said your target. So you know the spectrum X gamma is also volume limited in a sense, because it's designed to observe, you know, galaxy clusters, and the sensitivity is such that it will reach the redshift at which those galaxy clusters are expected to form. You know, there's nothing beyond that redshift in terms of observing galaxy clusters. In terms of observing those black holes, which almost fall into the intermediate mass range, right? So yeah, probably Lynx will be the first. There's nothing even close in sensitivity planned, you know, compared to Lynx. And frankly, Athena, Spectrum X Gamma, they don't even reach Chandra sensitivity limits.
That's quite spectacular. I hope it flies.
Thank you. Yeah, I hope to.
Yes. Wonderful. Okay. So thank you very much, everyone. Thank you, Alexey, for taking the time to
my pleasure.
Your project. Wonderful.
Thanks for wonderful questions. You know, they were spot on.
Yes. So our next scheduled talk in the Golden Webinars in Astrophysics series will be on November 13th, and will be given by Bob Williams from the Space Telescope Science Institute, who will be telling us about probing the distant universe with the Hubble Space Telescope. Right? So he will tell us about the initiation of the Hubble deep fields and all the deep field projects. So thank you again, everyone. Thanks, Alexey. Thanks, audience. Thanks, panel members. Stay safe, stay healthy, and see you at the next Golden Webinars in Astrophysics. Take care, everyone.
Bye-bye.
Bye.